Hello everyone, welcome to today's lecture in which we will have a little recap of last lecture in brief and then we will proceed with the remaining part of the oxidation. What we did last time was introduce Prevost reaction and its modification. As shown on this slide, that we start with a olefin like this, and in the presence of silver acetate and iodine we get eventually an trans or anti-diol. So, if one wants to get cis or syn diol like this, the Woodward modification in which water is added leads to syn or cis diol, and the main important intermediate was this intermediate here, which is a cyclic intermediate having a positive charge on the middle carbon here, and if the trans diol is to be obtained where there is no water used, the nucleophile, that is benzoate anion, attacks from the top, and in the case of syn diol to be formed, water attacks onto this particular carbon atom here. And this is the main difference that we had seen last time, and we saw that the attack of the iodine takes place from the side where there is less steric hindrance. For example, when we took a case something like this here the iodonium ion that is formed like this was from the alpha side, and this iodonium ion then gets attacked by the acetate ion from the beta side and forming an intermediate of this type. This is something that I had not elaborated last time. So, I want to show you how the cis diol is obtained, which is from the beta side. So, if the iodonium ion is formed from the alpha side as shown here, and that is because this group methyl group is beta oriented, then you get the attack of the acetate from the beta side and alpha iodo and beta acetoxy, this intermediate is obtained, which in the presence of silver acetate now forms an intermediate of this kind in which both the carbon oxygen bonds are beta oriented, which then water attacks onto this particular center, forming this intermediate, which then breaks off and eventually gives, upon hydrolysis, beta diol. So, the beta diol has come because of two reasons. One is that iodine attacks from the alpha side and the water presence is responsible for the beta diol formation, which is cis diol. On the other hand, when osmium tetroxide is used, as I discussed last time, since methyl group is beta oriented, the osmium tetroxide attacks from the alpha side and that gives alpha diol, and that is also cis, this is also cis, but then the stereochemistry is different. Now, this was something that we discussed it last time. Now, before I start on the silver carbonate silite oxidation, I also want to briefly mention about something that we discussed last time, that is conversion of a ketone into an enone using IBX. So, this is the IBX that we used And what I showed that if the ketone is in equilibrium with the enol, there is an electron, single electron transfer to the IBX, which leads to the formation of a radical anion here and a radical cation here. Now this radical cation then reacts by transferring a hydrogen radical to this radical anion, which forms this intermediate, and we get an oxonium ion here which loses a proton here to form the enone. Now like this, and of course the reagent eventually forms the iodosobenzoic acid. Now this proximity of the transfer of an electron to the IBX can also be alternatively explained, that you have the ketone like this, where the IBX, the negative charge on the oxygen, takes up the proton from here, and then this oxygen attacks onto the iodine, forming this intermediate. Now this brings the double bond in close proximity with the reagent, which is now having a bond between oxygen and iodine. Now you have a single electron transfer from here, double bond to this iodine, forming a radical cation and radical anion essentially joined to each other, and then you have the loss of proton from here by the OH minus and breaking of this particular oxygen iodine bond in a homolytic fashion to form, there should be double bond here. So and then of course the loss of iodosobenzoic acid. So this was an alternative way of explaining the same formation or conversion of ketone to enone. Now we go to the present Fetizon's reagent, which is silver carbonate silicate reagent system, which we discussed, we introduced last time. It is essentially useful for the selective oxidation of secondary and allylic alcohols. Now silver carbonate is adsorbed on the silicate. This R means Fetizon's oxidation involves oxidation of primary and secondary alcohols utilizing the compound silver carbonate, which is adsorbed onto the surface of silicate, which I discussed last time, which is nothing but mainly a silica gel sedimentary rock, and it was introduced by Fetizon, and that is the reason why it is called as Fetizon's reagent. It is a mild reagent suitable for both acid and base sensitive compounds. Especially it is useful for the conversion of lactols to lactones, which I will discuss in a while from now, from diols. The reaction is inhibited significantly by polar groups within the reaction system and also by steric hindrance of the alpha hydrogen of the alcohol. I gave this example last time, that if we have this allylic alcohol of this type, which is a secondary allylic alcohol or primary allylic alcohol or even normal primary alcohols, it is just that the reagent reacts faster with allylic or benzylic alcohols than with normal saturated alcohols, and but then still the reaction does take place. For example, here in this case, when symmetrical diol is taken and oxidation is carried out, the first oxidation gives the aldehyde, which is like this, and then there is an equilibrium between the hydroxyaldehyde and the lactol of this type, Now this is a secondary alcohol and this gets oxidized to form the lactone. Now here we have another diol, but then the difference in this diol and the above diol is that we have one allylic alcohol and one non-allylic alcohol. So as I mentioned earlier, the allylic alcohols are oxidized in preference to non-allylic alcohols. Therefore, in this case there are two possibilities, either this alcohol such the non-allylic primary alcohol gets oxidized or this allylic alcohol which is also primary can get oxidized. But then there is a preference for the oxidation of the allylic alcohol and eventually what we get is this particular lactone which is gamma butyrolactone. Now effect of there are stereo factors on this reaction. For example, if one takes a steroid molecule of this kind, this particular hydroxy group versus this hydroxy group, both are simple secondary hydroxy groups and both can get oxidized. However, this particular hydroxy group is close to this geminal dimethyl group and also it is in the midst of the ring, therefore it is sterically more hindered and there is a preferential oxidation of the hydroxy group which is on the top, leading to the formation of the ketone on this particular position. On the other hand, if one takes the steroid molecule like this which has two different hydroxy groups, one is this hydroxy group here, the other is this hydroxy group. Now relatively this hydroxy group here is less sterically hindered compared to this hydroxy group because this is away from the body of the system, ring system, whereas this is very close to the methyl group here. Therefore, there is a preferential oxidation of the hydroxy group which is here at this position and also it is allylic hydroxy group. So, there is a very clear steric effect on the oxidation of these alcohols with the Fetizon reagent. Now there are a few more examples which I want to show you here is that this particular molecule which has only one hydroxy group but with the hydroxy group which is alpha oriented, and in this case the only difference is that this is beta oriented. So as it has been found that this particular hydroxy group which is beta oriented gets oxidized faster than the hydroxy group which is alpha oriented. Now the reason for that is that if one looks at the conformation of this molecule, this is how the alpha hydroxy one looks like and this is the one where the beta hydroxy group is here. Now when we see alpha hydroxy, we have the hydrogen which needs to be oxidized is axial, whereas here it is equatorial, and this hydrogen which is axial is highly sterically hindered, and whereas this hydrogen which is equatorially oriented is less sterically hindered. So that is the reason why the oxidation of the beta oriented hydroxy group takes place much faster because the hydrogen is equatorially oriented. In a similar fashion, if one takes this particular molecule which is here, now has hydroxy group as axially oriented, but the hydrogen is equatorially oriented. On the other hand, the hydroxy group in this molecule is equatorially oriented, but the hydrogen here is axially oriented. So, the axis of the alpha equatorial hydrogen versus difficultly accessible axial hydrogen. So, this axial hydrogen is very difficult to get access of, whereas equatorial hydrogen here is easily accessible during the oxidation process, and that is the reason why the left hand side molecule having hydroxy group in an axial position gets 25 times faster oxidized than this particular molecule. Here now we have another example where we have a triol. As I mentioned earlier that the allylic alcohols are oxidized faster than non-allylic alcohols, but it also depends on many other factors. For example, here we have the stereochemistry orientation. Although this is an allylic alcohol which should get oxidized, but then what happens here is this particular primary alcohol gets oxidized first, and then there is a lactone formation which is then leading to the formation of this lactone via the corresponding lactol. So, here what we are trying to emphasize is that we have this particular position of the alpha oriented. So, what we will get is something like this and an lactol here. That means this primary alcohol gets oxidized first, and then the alcohol attacks onto the aldehyde to form this lactol. This lactol then gets oxidized, and this is mainly because of the cis junction here, or the cis junction of the cis orientation of the two hydroxy and hydroxymethyl groups. If we can compare this with this example which we discussed earlier, here oxidation does occur of the allylic alcohol faster, because that leads to the formation of the corresponding lactol and to the lactone. On the other hand, here the oxidation occurs only when the two hydroxy groups are cis to each other. Now we look at the mechanism of this reaction. There is a reversible chemiabsorption of the alcohol on the surface of the oxidizing agent, with the electrons of O, the oxygen, forming a bond with silver ions. Now I can show this in the next slide here, like this is how it is going to be forming. We have the oxygen of the alcohol, then forms a bond with the silver in this fashion. So there is a chemiabsorption of RCH2OH on the surface of the oxidizing agent, with the electrons of O forming a bond with the silver ion. Oxidation of the CH bond occurs, so the CHOH group is coplanar and perpendicular to the silver carbonate silide surface. This is exactly how it is shown here, that the hydrogen here, oxygen here, and this hydrogen here, they are in the same plane and they are perpendicular to the silver carbonate and silide surface. Then there is a concerted irreversible homolytic shift of electrons to generate reduced silver cations and hydrogen ions and a protonated carbonyl group that are formed. This is how it is here. So you have silver metal formed here, this oxonium ion that is formed here, and that then loses a proton to form the corresponding carbonyl group, and the homolytic shift which homolytic cleavage that has taken here leads to the formation of a hydrogen radical this hydrogen radical then donates an electron to the silver here, forming silver metal and of course a proton which is here. So, this is exactly what is written here. The considered irreversible homolytic shift of electrons to generate reduced silver cations H plus ion and a protonated carbonyl group are formed. Collapse to products with carbonate ions acting as a H plus ion acceptor to form carbonic acid that collapses to water and carbon dioxide. So, this is exactly what is shown here, that the alcohol interacts with the silver plus and the carbonate species will be just around with the other silver plus, and the silver plus of the first one interacts with the oxygen lone pair forming this intermediate, and then of course as I explained that eventually it is going to form this carbonic acid which loses carbon dioxide and water, and in the process we get one silver metal from here and then another silver metal from here. That is how there are two silver metals which are released from it. Now we can also see in a slightly differently that we have this substrate which is the alcohol. It is adsorbed onto the surface of the silver carbonate sealite reagent, and then we can think about transferring an electron from the oxygen to the silver plus forming a silver metal here and this radical cation. This radical cation then undergoes a homolytic cleavage here forming hydrogen radical, and this radical where when proton is lost from here we generate this diradical which collapses to form the ketone. Now this hydrogen radical which is ejected from here reduces another Ag plus to form second silver metal, and of course you release a proton from here. Now there is a loss of proton from here which eventually gives the ketone. So essentially it has the similar mechanism which I showed earlier, it is slightly more elaborate manner. So silver ions are adsorbed at the sealite surface, increasing the amount of sealites increases the rate by increasing the surface area. We can increase the amount of sealite which allows a more surface area to be formed, therefore the rate of the reaction increases, but it should also not be too much, otherwise dilution effects will dominate and that leads to the reduction in the rate of oxidation. As I mentioned earlier, primary and secondary alcohols are readily oxidized to the corresponding aldehydes and ketones under mild and neutral conditions, but primary alcohols are oxidized more slowly than the secondary alcohols. At the same time, as I explained earlier, allylic or benzylic alcohols are oxidized faster than the non-allylic or non-benzylic alcohol, and the reason for that is obviously very clear, that we have the formation of a radical which is here, and that is more easily stabilized when the position would be allylic or benzylic. This is an example where there is a primary hydroxy group as well as there is a secondary hydroxy group. When the reaction is carried out, there is a preferential oxidation of the secondary hydroxy group over the primary hydroxy group. It is useful for acid and base sensitive because it is a relatively mild reagent and therefore the conditions are easily useful for acid and base sensitive alcohols. Polar groups and steric hindrance retard the reaction. I already mentioned about the steric hindrance. Now let us see the polar effects. The rate of reaction of alcohols depends on solvent polar or non-polar. For example, solvents like acetone, ethyl acetate slow down the reaction because there is a comparison, there is a competition between the oxygen of the acetone and the ethyl acetate with the oxygen of the alcohol to attach on the surface of the silver carbonate sealite system. Now benzene is also used routinely, but it was found that when solvents which are less polar than benzene such as N-heptane are used, the rate is increased. It means that, it simply means that even benzene hinders the rate of the reaction because it has pi electrons, and therefore there is possibility of having a competition between adsorption of the benzene onto the surface of the reagent versus the adsorption of the alcohol onto the surface. Of course, alcohol will get adsorbed faster, but still there is little hindrance from the benzene. So one has to choose the solvent based on also the solubility of the substrate. But solvents like toluene, hydrocarbons and acetone are routinely used, and so are dichloromethane and chloroform, particularly for allylic and benzylic alcohols. Thus the solvent becomes very critical for as a choice for the reaction to take place. As we discussed, it also depends on the various kinds of alcohols, primary, secondary, allylic, etc. And we have here one very interesting example that this particular alcohol reacts 50 times slower than this alcohol. One can see that the presence of the double bond makes the difference between the two substrates where the oxidation, that means this pi bond like benzene can also compete with the alcohol for the adsorption at the surface of the silver carbonate sealite reagent system. So we will stop it at this stage and continue with the reaction of different types of alcohols with Fetizon's reagent in the next class. Meanwhile, you can read and try to understand what I mentioned and discussed in this class. Thank you.